So, now we can get back to the traveling salesman problem. So, now, back to the traveling salesman problem. And I'll just remind you what this was. So what are the aspects of a traveling salesman problem? In fact, this is a variety of problems which involve finding Hamilton circuits. And so what do we have? The key similarities. We have a traveler. So this is the person that you can kind of imagine walking along our graph from vertex to vertex along the edges. The person or vehicle or even a bee, because I think I mentioned that bees actually pollinate flowers according to like how they can optimally visit every flower efficiently, rather than just how quickly they see it, which I find quite interesting. So the person, vehicle, or bee that we imagine walking from vertex to vertex along the edges of G, our graph. Good. Second similarity is that they all have a set of sites that the traveler has to visit. Once and only once, because otherwise it's not efficient. Good. And finally, we have a set of costs. And remember, these are like weights on our edges. And we know all about what weights are now, so remember that weights are kind of like it's a positive number or a non-negative number. You could weigh 0, I suppose. So it's a non-negative number that we assign an object, and it represents some quality about that object, right? So a weight could be, it could be a physical weight. It could also be a speed limit. It could also be the cost of a plane ticket. It could also be the amount of votes you control in a voting system. All sorts of different things. So, yeah. So these are non-negative numbers associated with the expense of traveling from one site to another. And so we had an example last time. What was our example? It was recall our example. Our salesman must visit 5 cities, including his own, where he will start and finish his journey. And what he wants to do is find the cheapest way to visit every city exactly once. So what did we do? We drew a graph with vertices representing cities and edges with weights corresponding to the price of traveling between them. Okay, and so what that looked like was with 5 cities, if we have A, B, C, D, and E, and we drew a complete graph on 5 vertices. Oops. So we drew a complete graph on 5 vertices, and then we labeled the edges with $sign with costs. Okay? And I can't remember exactly what they were. I could go back and find them, but I don't think it's super important, because instead I'm going to show you some different examples. So yes, this is actually what I wanted to do. I want to go to our book and show you. So this is the example that I was using, and I think I took the prices directly from this graph. So if you take a look at this, it looks super different than my K5, but in fact you can see that yeah, indeed. Oops, sorry. We still have vertices A, B, C, D, and E. That's 5 of them. And every vertex has 4 edges coming out of it. 1, 2, 3, 4. Corresponding to the prices that it costs to fly from that vertex to another. And as long as we have 5 vertices and every vertex has degree 4, we know we have a complete graph on 5 vertices. So even though it doesn't look like it, we could drag these little points around and make it look like a star. Okay, but I also wanted to show you some other kind of fun examples. So this one, I guess, is a fictional example, so maybe a little less cool. But you could talk about the weights on edges not being amounts of plane tickets, but maybe the weights correspond to travel time between the moons. So if maybe it takes 8.1 years to get from Earth to Titan, you could use those for weights. And finally, this is quite cool. So I wanted to read this together. The story of the Mars Science Laboratory was introduced as a chapter opener. Curiosity is a 6-wheeled $2.5 billion rover loaded with cameras and instruments that roams around a region of Mars known as the Gale Crater. And so, yes, so we have this really expensive rover wandering around Mars, and the primary mission objective is to look for evidence of the existence of life on Martian soil. Curiosity is a slow traveler, about 30 meters an hour on average. And so because this rover is so slow, they want to make it optimally efficient so that the rover covers as much ground as possible. even when it's moving around slowly. It's such an expensive thing to be doing that they want it to be done efficiently, right? You wouldn't just want the rover wandering back and forth along the same path and not getting you any real new data. So in order to figure out how to most efficiently direct the rover from different sites, we'll say that 7 locations around the Gale crater. So these are kind of the 7 sites, G1, G2, G3, G4, and all the way through G7 that the rover has to visit down here on this graph. And all of the edges connecting them with the number of meters that it would travel. So all of these are examples of traveling salesman problems. So what do I want to do? I actually would like to... okay. I'd like to talk about some algorithms for solving these. How to solve a traveling salesman problem. I'll warn you, it's not easy. There's a reason why this is included in your course. It's because it's still an open problem. So we're looking for algorithms, really efficient algorithms for solving this, and we are not finding very many. So we need an algorithm. The first kind of algorithm to know is a brute force algorithm. These are kind of the most basic, most simple algorithms that you can know, and I mean they're kind of what they sound like. So the brute force algorithm is basically this. The procedure is just try every path, really. It's just, so how did I have this worded? Good. Check the cost of each possible circuit. And choose the lowest. So let me go back. Actually, I want to go and find this thing from last class when I drew out the thing. Good. Copy. Okay, so maybe I'll erase this and paste that in there. Okay. So using this graph, well, do we want to do a brute force algorithm? So just how many paths do we have? Before we just start checking different paths. Sorry. Hamilton circuits. We might like to know how many there are. So, how many are there? Counting Hamilton circuits in Kn. So, first observation. Our salesman can visit the cities, each city exactly once, in any order he chooses. In any order. Starting and ending at A. So if we count this, we could say, okay, so then, so from A, our salesman could go to B, or C, or D, or E. So that's 4 different options. Now, if the salesman goes from A to E, then the next option is either B, C, or D, right? And same, if he goes to D, then he's got B, C, or E, etc. So what we notice is that he's got 4 options for the first trip, 3 options for the second, 2 options for the third, and 1 option for the last because he needs to go home. So that means that, so i.e., so he can, in this version, we have 1, 2, 3, 4 different places he could go to begin with. Right? And then, say he goes to B. Now he has 1, 2, 3 different places he could go second, because he can't go back to A. And say he goes from A to B and then to D. Well, how many places can he go next? Either C or E, or nope, can't go back to A. So, because otherwise he would have visited that point twice. So he has to do A, B, D, and then either E or C, so that's only 2 options. Okay? So that's 4 options for first trip, 3 options for the second trip, 2 options for the third, and 1 option for the fourth. Okay, so in total, that makes there are 4 factorial equal to 4 times 3 times 2 times 1 different Hamilton circuits to check. How many is this? Oh, I should have written that. So 4 factorial is 4 times 3 times 2 times 1, which is 12 times 2, which is 24. 24 different things to check. That's not so bad, but it's still enough that I don't really want to do it. I won't sit here and do it for you by any means. So on 5 vertices, 24 things to check is not so bad. But already in this other example, So in this one, we had 1, 2, 3, 4, 5, 6, 7 different vertices. But for the Mars rover, with 7 different sites, there are 6 factorial. 5 times 4 times 3 times 2, 1. So that's 24 times 5 is 120 times 6 is 120 times 6. That should be 600 and 720. 720 options to check. For a computer, that's still not bad. But 10 factorial? This is more than 3 million. Okay. So that's a lot. So maybe we want a better strategy. Maybe we want a better strategy. Because brute force is quite inefficient. And what I mean when I say inefficient is that the effort needed to solve the problem grows disproportionately to the size of the problem. Disproportionately should have gone on the next line. Isn't that great? Normally you can't do that. Disproportionately to the size of the problem. Okay, so let's try a different one. 2. The nearest neighbor algorithm. Okay, so the nearest neighbor algorithm is, again, it's just what it sounds like. So this one, the procedure start, so from the starting vertex, choose any neighbor. Okay, and from there, you're always going to choose the, nearest neighbor. So, start at the designated vertex, and at each step, visit the nearest neighbor, which is not yet visited. So this will give you a Hamilton circuit because you're just not ever visiting one vertex twice. So this will give a Hamilton circuit because no vertex is visited twice. And that's all. Yeah. as long as you keep on not visiting any vertex twice, and you're on a complete graph, on a complete graph, this always works. The problem with this one is that it might not find the cheapest route. So I'll just show you what I mean by the nearest neighbor. I mean on a complete graph, it's really quite simple. You just start at the vertex, starting one. Go to any neighbor. Then go to the nearest neighbor, either E, B, or C. I'm going to say C. Then go to the nearest neighbor, E. Then go to the nearest neighbor, B. Then go to the nearest neighbor, well, back to A. All of the other ones have been taken up. So that one's really simple. The third one is going to be maybe a little better. For this, we might like 3. The cheapest link algorithm. So the cheapest link algorithm is like the nearest neighbor, but you're looking for the cheapest link. But at every step, choose the cheapest edge possible. So this is better, but what's interesting is that it still doesn't get you the right answer every time. So let's put the graph back there, and so what this is going to look like is, wonder if it will do it for us. The cheapest link algorithm. So we start at A, and then we go to E. Actually, oh sorry, I want to do something else first. Before explaining the algorithm, we need some observations. Okay, so the first observation is what we call the partial circuit rule. And what this says is that a Hamilton circuit cannot contain any partial circuits. So what's a partial circuit? So a partial circuit is like if this is our Hamilton circuit here, around vertices like that. What we're saying is that if that's a Hamilton circuit, then this is definitely not a Hamilton circuit. So we'll go over there, and then over there, and then this one, and then this one, this one, this one, this one. So this is what we call a partial circuit. So it's like a circuit inside the bigger circuit. And you see that, so this is a partial circuit. And it's kind of clear that a Hamilton circuit can't contain one, because that would mean visiting this vertex 3 times. If you have 3 edges coming out, you leave that vertex, you go back to it, and you leave again. So this would correspond to visiting the same city twice. Okay. And the second rule is the 3-edge rule, which again is pretty similar. It says that a Hamilton circuit cannot have have 3 edges coming from a vertex. And so what that one means is, like, if we have 3 edges coming out, well, I mean, the big thing here is that every circuit, on every circuit, every vertex has exactly degree 2, because you go in and you come out. And it doesn't matter how you draw a circuit, a closed path, whether it's like that, or like this, every vertex is going to have degree 2, because it goes in and then it goes out again. Okay, so that's the idea, is that now it doesn't matter what we do. Maybe we could go around here, visit some other vertices, go back and visit that one, but now we contain a partial circuit. Okay. So now we can do the cheapest link algorithm. Says 1, from the starting vertex, choose the edge of least weight, smallest weight, or cost. Okay, and at each step, choose the edge of lowest cost as long as neither rule above is violated. And that's it. 3, this terminates by returning to start after visiting the last vertex. So this is pretty good. This is the best one we've got so far. This is the best we've got so far, but it isn't perfect. Sometimes even this algorithm fails. Okay, so let's do an example. Okay, so our starting vertex was A, right? A is our start. Now, from A, we want to choose the path which has the lowest cost. So, I look at the costs and I see that this is 133, this is 152, this one's 119, and this is 185. So I think that the best thing to do is to go from A to C for 119. So, step 1, take A to C for 119. Okay. The second one, I'm going to look at all the others and I'll see 121, 171, 120. Those are my three options. 120 is the cheapest. So now the thing to do though is, do I look, if I was going to take this edge, would I break either the 3-edge rule or the partial circuits rule? So no is the answer, because I just look at the red edges, and in the red edges there are 1, no circuits, and 2, every vertex has either degree 1, like this one, or degree 2, like this one. Okay, so I will take this edge from C to E next. Next, oops. So doesn't, and I'll do this for the next one. Okay. So next we want to look at the cheapest ones. So from E, we have an edge for 133 back to A, an edge for 199 to D, and an edge for 200 to B. But so we would like to take the 133 one. But look what happens. If we take the 133 edge back to A, we make a partial circuit. And that's not okay. So, next, can't take E to C without making a partial circuit. So for that step, so choose, what do? We go to D, because D is 199 instead of 200. So instead we go down to D. Oh, 199. Okay, and finally, we only have one more place that we can go, which is B. Because if we go back to A, we make a partial circuit. And if we go to C, we make a partial circuit. See, if we took this edge to C, then we would also make a partial circuit there, and that's not okay. So we're going to take the edge to B, and then back to A to finish our journey. Then D to B for 150. And back to A for 185. Okay, so total cost of cheapest link algorithm starting at A is 119 plus 120 plus 199 plus 150 plus 185, which makes 18, and 5 is 23, 4 and 5 and 14 and 19 and 27. Finally 2, 3, 4, 5, 6, 7. Okay, so this cheapest link algorithm costs us 773. But what I want you to look at is, but we found a cheaper version last time. Remember what we did? We looked just for like the cheapest edges that we could see, and we kind of selected them one at a time, and then just kind of saw what could work. This is kind of like guess and check. So if we want to have like this edge in there, and maybe this edge, and this edge. Oh yeah, that was the one. If instead we took the 121 one up to B, instead of the 120 over to E, then we could have taken this 150 there, and this one there, and I think that that actually sums up to something less. So there we have 133 and 199 and 150 and 121 and 119. That makes 10, 14, 12, 13, 18, 19, 20, 21. So we actually have a cheaper algorithm. So there, not a cheaper algorithm, but there is a cheaper solution than the cheapest link algorithm provides. And that's important because this is actually the best algorithm that we've got for solving these problems at the moment. And it's such a simple sounding problem, but yeah. But this is the best efficient algorithm that we've got. And I'll make a note, it's efficient because it finds its optimal solution first try. Efficient because it finds its solution first try, while brute force compares every option. So this is kind of, it's not paradoxical, but it's interesting that the brute force, it takes so long, but it's the only way that we know to find the cheapest way to travel. And this is really, like, airlines are working on these problems. They would pay you a lot of money if you could if you could get a new algorithm to calculate, cheapest flights. I mean, maybe not airlines, places like Kayak, right? So wouldn't that be a great thing for them? But yeah. So in conclusion, brute force is the only algorithm we know that finds an optimal solution. Others come close, like cheapest link, but it is still an open problem whether we can do better. So some problems aren't still open in that sense, you know, like our voting system things. We can sometimes prove that we'll never be able to have a really fast algorithm, but in this case we haven't. So yeah, I think that's a good note to leave you all on, because things to think about. You could be the person that solves this problem, or you could not be. But I hope I hope you've enjoyed my lectures. I've really enjoyed giving them. So yeah, hope to see you all in person again on campus next semester. And yeah, I hope this has been a good one for you. All right, until next time, enjoy. Bye.